Hi, thank you to the organizers for inviting me to the L2ID workshop. I'm very happy to share our recent effort on compact transformers, a new design and usage of transformers that we hoped that can be helpful to democratize AI by escaping the big data paradigms. Most of us will easily agree that transformers are one of the biggest things in computer vision and AI in the recent 3 years. Huge success in natural language processing since the new risk paper, attention is all you need. And then there's a set of quick success in computer vision in the past year or so. For example, the vision transformer paper we're showing here, and the DETR work from Facebook for object detection, and transformers have really great potentials. However, as many of you might have already observed, there is a very concerning trend in transformer-based research. They are extremely data hungry and compute expensive. Just a couple of years ago, we still think that ImageNet is a large-scale dataset. But what we used to call large-scale are no longer large-scale in the era of transformers. For example, on the left, you can see Google's internal dataset. The GFT dataset has 300 million images, comparing to the 1 million images of ImageNet. And the computing paradigm has shifted as well. Transformers benefit from big datasets and the large models for pre-training. The models can be billions of parameters. And the cost of training such models, don't even mention the hyperparameter tuning part, are only affordable by the lucky few at the large industrial companies like Google and Facebook. And there is less means for other researchers to verify the research results, and we have to take these results for granted. And most of the time, we don't even have the chance to test the models, don't even mention reproducing them. And these trends are very concerning. And these concerns motivate us to democratize AI research for transformers. And in particular, our research aims to help 3 different groups of people. First, we want to help those beginners with very limited resources to be able to play with the transformers. And secondly, for serious researchers and those who are less fortunate do not have access to thousands of powerful TPUs or huge datasets which are only accessible internally at large companies. And lastly, we want to help those people who are dealing with important problems that are applicable only to smaller data sets. For example, in medicine and science, and people sometimes are only able to collect a very small amount of samples for different events. And to achieve this goal, and to return to the very good and old CIFAR 10 dataset on the right side. And it has only 60,000 images with a resolution of 32 by 32. And on this dataset, the numerical results are still meaningful for research, but the scale of the dataset is small enough so that a regular person can reproduce the approach and play with it with even limited resources. And the next chapter of the talk will be following this outline. So we will first revisit the vision transformers and the big data paradigm, and we will introduce our proposed design of our compact transformers, including 3 different variants: the VIT Lite, and the CVT and the CCT. And finally, we will share some of the encouraging experimental results from our compact transformers. The original vision transformer was introduced in the paper An Image is Worth 16 by 16 Words, which was published in iClear 2021. And the work passed the patches of the images through a transformer encoder and then classify them. So the design is relatively simple and elegant. And a little bit more about the patching and the embedding process of the vision transformers. So our image is worth 16 by 16 words because we can break the image into patches of 16 by 16. And we can then flatten the images and embed this into a fixed number of dimensions using a linear layer. And this is actually equivalent to a 16 by 16 convolutions with 16 by 16 kernels and the 16 by 16 strides. And the patching operation is equivalent to the sliding window operation in convolution, and the linear projection is equivalent to the convolutional filtering process. Besides the patch-based tokenization, there are several other designs in the vision transformers that are worth noticing. There is a class token fed into the transformer encoder, and there is a MLP classification head after the transformer encoder, and it sits on the left side. And there's a positional encodings added to the patch embeddings before the transformer encoder. And let us quickly examine these components. Let us first look into the class token and the classification head. So there is a nullable classification token prepended to every sequence of the patches, and it is a d by 1 dimensional vector, just like the rest of the patch embeddings. And after applying the positional encoding to the sequences, and they are jointly fed to the transformer encoder, which outputs this n plus 1 by d dimensional vector, where n is the sequence length. And at the final classification stage, only the first 1 by d row of this n plus 1 by d dimensional vector is taken and fed into the final classifier. And that's why the MLP head is sitting on the left. And in the bottom, we have a diagram showing the overall pipeline of the vision transformers to better visualize the design of the VIT structure. And the classification head is represented by the slice operation and the linear layers. Positional encoding is also an important component of the vision transformer design. And much like the original transformer architecture for NLP, the positional encodings are added to the sequences for the embedded patches of the image. And the vision transformer used the learnable positional encoding as opposed to the sinusoidal encodings. And the positional encoding improves the accuracy because the positional embeddings are added to the patch embeddings to retain this positional information, which are missing by the patching operation. After looking at the overall design of the vision transformers, let us briefly inspect the big data paradigm associated with the vision transformers and the other types of transformers. So, vision transformers has achieved a really great performance on the large data sets like ImageNet, but it was pre-trained on the GFT 300 million dataset and then fine-tuned on the ImageNet in order to beat the convolutional counterparts. And when in the original paper, when we trained this from scratch on the ImageNet, the results were slightly worse compared to the convolutional counterparts. And we did some pilot study. So if we do this on a smaller data set using the VIT-based model, and we can achieve only 69.82% top 1 accuracy for the CIFAR 10 dataset. And this is very low compared to the transfer learning results where we are getting over 99% accuracy. And why is this? In the original paper of the vision transformers, the authors explain that transformers lack some of the inductive biases inherent to CNNs, such as the translation equivalence and the locality, and therefore do not generalize well when trained on insufficient amount of data. And this big data and the computing paradigms raise various concerns. And the two big questions we have here are, why do transformers have to be so big? And are such giant models always the solution to our problems? And the second question is, are we always in possession of such large data sets, or are we always dealing with the problems associated with so much data? And the answers to both questions are apparently no. Our recent work, the compact transformers, partially addressed these two concerns and help us to democratize AI by making transformers more accessible to those with limited computation resources and works on smaller data sets. So when designing the compact transformers, we have three objectives. First, we want to create compact and efficient transformer modules that is accessible by people with less compute and data. And secondly, we want to build transformers that can work well on smaller sets of data. And lastly, we also want to leverage and to unite the convolutions and the transformers design, especially in the tokenization step, to introduce proper inductive biases that might be helpful to vision problems. To design compact transformer models, a first thing that we can do is to make it smaller and compact. And we can do this literally. So we can propose models with fewer transformer encoder layers, with less multi-head self-attention heads, and with the smaller dimensions of patches. And in fact, we designed very lightweight vision transformers with as few as 200,000 learnable parameters, and it still works relatively well. And in addition to make transformer models more compact directly, we can also design a novel sequence pooling technique here to remove the needs of the class token. So instead of prepending a d-dimensional class token vector to the sequence, we place that vector as a d/1 linear layer after the transformer encoder. It therefore maps the n by d output matrix to an n/1 vector. And then we apply softmax to the n/1 output, transpose it, and multiply it by the original n by d output from the transformer encoder. And this will result in the 1 by d output. We pull over the entire sequences of the data, since this contains the relevant information across different parts of the input image patches. And this makes our model more compact and also potentially more accurate. And this 1 by d vector is then taken and fed into the final classifier, just like in the original vision transformers. And this sequence pooling technique matches our model's performance with the light version of the vision transformers in terms of the number of parameters. And in terms of the complexity, it is actually slightly less. And this makes the whole model more compact and accurate. And the design is illustrated in the diagram below. Another key piece of our compact transformer design is the incorporation of convolutions in our the CCT variants of the compact transformers. So patching and embedding is already a convolution in itself, even though they are non-overlapping, and it requires the input image to be divisible by the patch size. And then why not we just try overlapping convolutions? By having shallow convolutional layers at the input the tokenization stage, not only are we able to make our models more flexible about input image sizes, and the inductive bias introduced can also make our model more efficient in learning and more accurate in the final results. So here comes again our compact transformer design, and we are showing the two different variants of this compact vision transformers on the right side and the compact convolutional transformer on the left side. So if we replace the sequence pooling with the classification token for the compact vision transformer, so it is basically the lightweight VIT, or we call it VIT light in our compact transformer variants. And both the CVT and the CCT use the compact models and the sequence pooling. And the difference between these two variants are in the tokenization step, where CCT used the convolutional tokenization and the CVT used the patch-based tokenization, just like the original VIT design. So let us look at some results to see that if we are able to achieve our original goals. And on the left, that's the large model from the VIT base. It is a huge model with 86 million parameters, and it has the 16 by 16 image patches, and it achieved 69.82% top 1 accuracy, which is relatively low. And with the right patch size and the compact design, with the right tokenization and the sequence pooling technique, and some additional data augmentation and optimization, we are able to boost the performance for CVT and the CCT to over 90%. In particular, the CCT's performance, the 94.81%, is on par with the convolutional models with a similar amount or even smaller amount of parameters and the computational operations. So let us dive deeper into some details of the experimental results of different variants of compact transformers and see what we can learn here. So for our VIT Lite variant, our first strategy is to make the models smaller. Not all images are 16 by 16 words, and we should build models with the right size for smaller datasets like CIFAR 10. As you can see, comparing to the 69.81 baseline model we mentioned earlier, we can boost the performance of the VIT Lite to over 90%, which to some extent demystify the myth of transformers are always data hungry and can only apply to large data sets, or that we always need large models. And one note here is that you can easily train our compact transformers on CPUs. On top of our compact transformers variant, the VIT Lite, we can make the model more compact by removing the class token, as mentioned earlier, to leverage the novel design of the sequence pooling. And as it can be seen from these tables, the sequence pooling is able to improve the accuracy significantly comparing to the original VIT Lite design, and it have the exact same amount of parameter as well. Our third variant, the CCT model, the convolutional variant, takes the performance of the compact transformers one more step further. By incorporating this convolutional inductive bias in the tokenization step, and we only introduced a small amount of overhead and a small amount of additional parameters, but we are able to achieve much better performance. And you can see here, our small model with only 284,000 parameters can get an accuracy almost 90%. And again, you can train these models on any modern CPUs and get the good accuracy very quickly. An interesting phenomenon that we discovered, and it is worth mentioning here, is that our CCT variant, comparing to the other variants, are less dependent on the positional encoding. Even if we remove the positional encoding for the CCT variants, the accuracy will not drop too much. And this is especially true when we're comparing to the VIT Lite and the CVT models. And this is partially due to the incorporation of the convolutional inductive bias, and the positional encoding becomes less relevant. Besides its effectiveness on smaller datasets, our compact transformers works on a large dataset as well. So in our initial experiments on ImageNet, when training from scratch, we find out that when we only use 200 epochs, which is two-thirds of the original number of training for the VIT work, and we are able to achieve almost 1% better accuracy on ImageNet. And our model is only a quarter of the size of the original VIT base, which is 86 million parameters. And finally, our compact models work not only on computer vision, but it works on tasks beyond computer vision. In our initial experiments on the NLP task like text classification, we can obtain better results than the light transformer variants with much more compact models. And there are more details regarding these results. The code and the models can be found on our GitHub repo or our updated archive paper. To summarize, so in our effort to democratize AI and escape the big data paradigm, we designed the compact transformers, and it works well when training from scratch on small datasets like CIFAR 10. And the key takeaways from this design is that not all images are 16 by 16 words, and the patch size matters. And the sequence pooling can eliminate the class token and make the model even more compact and more accurate. And finally, the convolutional tokenization can help boost the performance and make the model less dependent on the positional encoding. And our compact transformers works both on computer vision and NLP tasks. And our compact transformers are easily accessible, and you can run this on CPUs. We have some additional resources linked here. So we have a Colab notebook, and we have a GitHub repo where you can find everything. And we also have an archive paper. You can read more about our design and our experiments. And finally, thanks to the sponsor of the research, and thanks to my students who owns all the credits: Ali Hassani, Stephen Watton, Nikhil Shah, Abdulkarim Abdulwali, and Justin Lee. And thank you for listening to the talk, and I hope you enjoy playing with the compact transformers on your laptops.